In the last couple of classes, we looked at gradient descent in some detail, and we saw at what rate gradient descent can converge to the minimum. All of this was for convex functions with additional assumptions, either smoothness or Lipschitz continuity or strong convexity, right? But typically what is used is not gradient descent, but something that's closer to stochastic gradient descent. And towards the end of the last class, I said why we don't employ full gradient descent. The reason again boils down to complexity. Recall that our goal is to solve some form of a regularized empirical risk minimization problem, where we want to minimize a function of the form 1 over n summation I equal to 1 to n, some fi of w, where this where the ith function fi is going to correspond to the loss for the loss function for the ith sample, right? Plus some regularization term. But this regularization term is anyway going to be common for all of these fs. So you can take that separately. Now, if we want to do full gradient descent, then to find the gradient of f, we need to compute the gradients of fi, and there are n such gradients. So the overall computational complexity of finding the gradient of f for one time step is going to be something that scales with n, the dimension, and as well as the number of iterations. Right. So in each time step, I need to incur a complexity of omega n, right, which is very expensive, and it also means that I have to go through the entire data set every single time. And for a data set that has, let's say, millions or billions of data points, it's very expensive. So the common solution, which is stochastic gradient descent, is to replace the gradient of f with some random vector f prime, with the property that in expectation, this f prime is equal to the gradient. Right? And the randomness involved over here is independent of everything else. In particular, the assumption in stochastic gradient descent is that you're using independent randomness in every iteration, and you're using randomness that is independent of the data that is provided to you. Okay, so typically when someone says stochastic gradient descent, that is what they mean. We'll see that this doesn't really hold in when we are actually doing SGD type algorithms for machine learning. So a very common approach is the standard or classical stochastic gradient descent is where you choose a sample from the data set uniformly at random with replacement. And if you do this, then it's very easy to see that the stochastic gradient in expectation is going to be equal to, so the stochastic gradient is equal to the gradient evaluated on that random point. So in expectation, the stochastic gradient is equal to the true gradient. What is more commonly used is some variant of mini-batch stochastic gradient descent, where you choose B samples uniformly at random. And again, these are typically drawn with replacement. So that if you do that, then again, you'll have the stochastic gradient being equal to the average of the gradients on those B points. And in expectation, again, this is going to be equal to the true gradient. Okay. So this is classical stochastic gradient descent, or classical mini-batch stochastic gradient descent. And for this, you can again prove similar convergence rates. In fact, a lot of the derivations that we did for gradient descent can be tailored to derive convergence bounds for stochastic gradient descent, at least in some of these cases. It's not very hard to do so. Now, all of this that we discussed so far was for convex functions. But in practice, particularly in machine learning, you don't have this property of convexity anymore. And to see, at least visually see, why the loss function in training deep neural networks is not convex, let's take a very toy example where we have a feed-forward neural network, a two-layer neural network with one hidden layer. right? So you have two inputs. So the input is a vector in R2. There are three hidden neurons. So basically what we have is HW of X is equal to P of, let's say phi2 of W2 transpose of phi1 of W1X. So the inputs are multiplied with some matrix W1, and to that you apply this activation function phi1 to get these activations theta1, theta2, and theta3. And to this vector theta, you multiply with W2 transpose, and then finally apply an activation function to get your output. Okay, it's a simple example. Now let us say that, now remember, what are the trainable parameters? The trainable parameters are essentially the weights corresponding to each of these edges, right? Hopefully you're all okay with that. Now, let's suppose that for some values of these weights, you get the gradient of whatever HW to be equal to 0, or the gradient of the loss function to be equal to 0. Okay, so there's some configuration or some values of these Wi's for which you get the gradient equal to 0, or that corresponds to either a local minimum or a global minimum. Okay. Now let's say that I keep everything else the same, but I just permute the weights. Okay. The entire neural network is exactly the same. The function that it computes is exactly the same, but I'm just relabeling the hidden unit 1 with hidden unit 2. Right. Now, the overall function that is computed for the same inputs is exactly the same because nothing has changed in the network. All you have done is just a relabeling of the, or in other words, a reordering of the variables. Okay. So even for this set of weights, the gradient is equal to 0. So this is also going to correspond to a minimum, right? So if this configuration achieves a minimum, then just a reordering or a relabeling also is going to correspond to a minimum. And all of this is arising because of this symmetry in the architecture, right? Because whatever is computed by this set of weights is also computed by this set of weights. Because the overall function is the same, how you label the variables are just changing. The order of labeling just changes. So for the same, particularly for feed-forward neural networks, you don't have just one global minimum. You are going to have multiple global minima, and the number of global minima is going to scale faster than exponential in the number of hidden variables. Because even here, in this very simple toy example, you can see that the number of global minima is going to be the number of ways in which you can reorder these hidden neurons. And there are three hidden neurons, so there are 3 factorial ways. Right? So there are at least 3 factorial global minima. Okay? Now again, I'm making some assumptions in that all of these are distinct global minima. It's possible that not all of these are distinct global minima because a relabeling could potentially give the same set of weights. If, let's say, all of the weights are equal, then a relabeling doesn't change anything. You get the same point. Right? So there could be as large as 3 factorial. In general, if you have, say, k hidden neurons, then there'll be k factorial many global minima. Right? So even in this simple toy example, you can see that there are a large number of global minima. It's highly non-convex. Okay? And that is what makes deep learning challenging, or optimization for deep learning very challenging. And a lot of the counterintuitive phenomena occur precisely for this reason, because, well, you're trying to run gradient descent or stochastic gradient descent on a highly non-convex function. you don't know what it is going to converge to. You don't know. There are a very large number of local minima and also global minima. So if you initialize from a random point, how do you know that, first of all, is this going to converge to a local minimum? And if it does, how do you know that it's a good local minimum? Right? Because in the end, our goal is not just to minimize the um, to just minimize the loss function, right, or the empirical risk. During training, what you're doing is minimizing the empirical risk, but our end goal is to minimize the generalization error and not the empirical risk. So how do you know which of these local minima or global minima is going to correspond to something that minimizes the generalization error? That's something you don't know in advance. All right. So what can we say about gradient descent or stochastic gradient descent for non-convex? So as it turns out, what I talked about so far was just global minima and local minima, but there can also be saddle points, as we also alluded to in a previous lecture. So when the function is non-convex, there could be a large number of saddle points as well. But it turns out that if you randomly initialize the point for, let's say, gradient descent can be shown to eventually converge to a local minimum. But what can potentially happen is that it can be stuck in a saddle point for a very long time. So what can happen is that it starts from the initial random point. It can go somewhere close to a saddle point, stay there for a very long time, and then eventually come out. Again, this depends on the function, because potentially, like what happens in a saddle point? In a saddle point, there are some directions in which the function increases, and there are some directions in which the function decreases. Now, let's say that there's only maybe one direction along which the function decreases, which is where you want gradient descent to eventually go to. But perhaps the curvature in that direction is not too large; it's very less. So what can happen is that it may take a very long time to find that direction and eventually escape the saddle point. It may be stuck there for a very, very long time, right? But there are ways of um, mitigating this problem. It turns out that for sufficiently nice functions, what you can do is use perturbed gradient descent. So add a small amount of noise when you get close to a point that is either a saddle point or a local minimum. If it's a saddle point, it will escape that saddle point fairly quickly. If it's a local minimum, then it will be stuck there, right? So this perturbation, it can just be just random Gaussian noise, nothing fancy. So if you add a small amount of Gaussian noise, then it can be made to escape the saddle point, basically find that direction along which the function eventually decreases fairly quickly. And you can show that the number of steps, additional steps that you require is something that grows roughly logarithmically in the dimension of the problem. All right. So there's a lot of recent exciting work in this particular area. How do you escape saddle points efficiently when the function is non-convex? And it turns out that even without any perturbation, under maybe slightly more assumptions on the objective function, just plain stochastic gradient descent can escape saddle points roughly at the same rate. But if you add a little perturbation, maybe it can escape even faster. All right. So let's maybe see a sort of numerical example as to what happens in gradient descent and stochastic gradient descent. So here's just visualization of both gradient descent and SGD for a simple, let's start with a simple quadratic objective. Okay, so we want to minimize a function of this form, f of x is equal to x transpose bx for some matrix B. And as we saw in the previous class, this function is convex only if B is positive semi-definite. And it's strongly convex as long as B is positive definite. Okay. We also analyzed if you recall, we also analyzed the rate of convergence of gradient of stochastic grade or of gradient descent. uh, in the strongly convex case, and we proved that the rate of convergence basically depends on L by mu, which is the condition number. So if the condition number is large, then it takes longer for gradient descent to converge. And if the condition number is small, it's close to one, then gradient descent converges faster. And for the quadratic objective, we saw that this condition number is basically just the ratio of the largest eigenvalue to the smallest eigenvalue of the matrix. So to just illustrate that, let's take a matrix B, which is of the form Q times D times Q transpose, where D is a diagonal matrix and Q is an orthogonal matrix. So I can really choose the eigenvalues according to my specification. All right. Let's start with both the eigenvalues being the same. So condition number is exactly equal to 1. Okay. So again, this is what the objective function looks like. These circles essentially denote the level sets. So along this circle, the value of the function is exactly the same. Okay, so it's a function in two variables, x1 and x2, and along this circle, the function value is exactly 4.6. Here it's 1.9 and so on. Okay, and this is initialized from some point, and you can see it just directly gradient descent from the beginning moves along the direction of the minimum. Stochastic gradient descent, on the other hand, okay, this is not exactly stochastic gradient descent. This is just perturbed gradient descent, because what I've just done is taken gradient descent and added a little bit of noise. Okay, so it's noisy gradient descent rather than actual stochastic gradient descent, because my objective function is um, just a quadratic, nothing else. So you can see that gradient descent, it starts from this initial point and just stops somewhere close to the minimum. Stochastic gradient descent, on the other hand, goes somewhere close to the minimum and keeps jumping around. And this gives the rate of convergence. So gradient descent it converges at sort of an exponential rate. This is in the log scale, whereas stochastic gradient descent converges at a slower rate. Right? Let's take the. Okay. Let's now see what happens for a non-convex objective function. It's a function in again in two variables, but it's a polynomial of degree 4. It has two local or two global minima, one over here and one over here, and it has a saddle point at 0, 0. I've initialized it from some point over here, and gradient descent, it sort of converges to the minimum. Stochastic gradient descent also seems to converge roughly at the same rate. Now, let me change a few parameters to begin with. Again, going back to the first example, let's say that I take the diagonal entries to be a little bit different. So now I took one of the eigenvalues to be equal to 1 and the other eigenvalue to be equal to 0.2. So right now the condition number is 1 divided by 0.2, which is 5. Still, again, it depends on the initial point. So let me maybe change the initial point. Right. So I started with a different initial with essentially the same initial point. I didn't change the initial point, but again the curvature now changes. So the rate at which it converges to the minimum depends on, of course, it's at the same Euclidean distance to 0 comma 0, but depending on where you choose the initial point, it can take a very long time to converge. All right. So let's take this example versus the same, but essentially just rotated. Right here, it seems to converge much faster, whereas in this case, it takes a much longer time to converge. All right. Um, and again, you can see what happens when you, let's say, increase or decrease the learning rate, and the variance of the stochastic gradients. So let's say I slightly increase the learning rate and maybe increase the number of steps of gradient descent to 35. I'll do the same for stochastic gradient descent and maybe double the scale of the noise. All right. So again, it converges at the same rate, but it's taking roughly the same rate, but it's taking a long time. It hasn't gotten close to the minimum yet. Right. So again, the you started from the same distance from the minimum, but now because the curvature of the function changed, it took much longer. For the non-convex objective, I can again change the initial point. Let's say I start from a point that is very close to the saddle point, right? Even then, I mean, this function is reasonably nice because there aren't too many directions to choose from. So even if I start from a point that is very close to the saddle point, it will still go to one of the minima. All right. It's typically in high dimensional cases where it can take a very long time to escape the saddle point and go to the minima. Okay. Any questions so far? You said the perturb GD you're adding noise to it. Correct. To escape the saddle point. Okay, in this case, even without perturbation, it escapes. So as I mentioned, GD will escape the saddle point, right? So as I said, it will eventually escape the saddle point, but potentially it can take a very long time. And it takes a very long time in high dimensional problems when there are too many directions to choose from, and maybe there's only one direction along which the function actually decreases. In this case, it's just a two-dimensional problem, so it will just escape the saddle point easily. The derivative will be equal to 0, yes. So I'm not sitting exactly at the saddle point, remember. I'm somewhere very close to the saddle point. I agree. If I start at the saddle point, then I'll be stuck. Right? Let's take 0, 0. So gradient descent is stuck here. Okay. But if I move a little bit away, say 0.007. Again, it's basically stuck. Right, so now you can see it's yeah, it's jumping very close to the saddle point itself. It's not able to escape the saddle point, but maybe but that's also because I initialized it in the wrong direction, so to speak. So let's say I do the same 0.0 but 0.001. Now it's escaping, right? Because it was a little bit to the right. Okay, so if I move a little bit away from the saddle point to the right, then it's going to find the minimum. Or if I move a little bit to the left, if I move it a little bit above or below, then that's a very bad direction. Right. So yeah, unless you initialize it along that line, it's going to find the minimum eventually, even just plain gradient descent. But again, in high dimensional problems, it's much more difficult because it can keep jumping around the saddle point for a very long time. Any other questions? Okay. So what I said so far was that in classical stochastic gradient descent, what you do is you sample each mini batch independently and identically distributed with replacement. But in practice, whenever you're training a machine learning model, that is not what you do. So in practice, what you typically do is you randomly partition the data set. So you take the data set and essentially you just shuffle the order of elements in that particular data set, and you run through this shuffled data set in batches of B elements each. Right? So basically you're sampling batches with you're sampling them without replacement. Okay, and this is treated as one epoch. Okay, so you run through this entire data set once in batches, and you get a total of number of samples divided by B iterations of gradient descent or stochastic or some variant of stochastic gradient descent. And then once you hit the end of the data set, you again randomly shuffle the data set. And that's another epoch. Okay, so your total iterations of the stochastic optimization problem is divided into multiple epochs. In each epoch, you run through the entire data set once. And in one epoch, you're basically sampling B elements with replacement. I'm sorry, without replacement. Now, is there a problem? Is this different from stochastic gradient descent? What do you think? If yes, why? If no, why not? Like what goes wrong? What are the assumptions in stochastic gradient descent? What assumptions do we make about the stochastic gradients? Okay, they have to be independent, which again we're immediately losing, because when we are sampling without replacement, then it's no longer IID. The stochastic gradients are not well, they're not IID per se, but they're not independent across iterations. They're dependent. And secondly, we may not even have unbiasedness. It's typically biased. In fact, I leave it as an exercise. Prove that this is biased. That is expectation of, um, let's say that what you get is f prime of wt, given wt in the tth iteration, is not equal to the gradient of f evaluated at wt. Is it clear that this is not or is it clear what the difference is between this random reshuffling and stochastic gradient descent? Although, like, if you read books or papers, typically they will call this random reshuffling also stochastic gradient descent. But to be precise, it is not. But anyway, even in this course, we'll call it stochastic gradient descent. But keep in mind that what we're doing is random reshuffling and not stochastic gradient descent. So in each epoch, you repartition the data set or you reorder the data set. But as it turns out, this random reshuffling can do better than stochastic gradient descent. For many classes of functions, you can prove that the rate of convergence of this random reshuffling is faster than that of plain stochastic or mini batch stochastic gradient descent. So that is why people employ this in practice. So empirically, this performs better than sampling with replacement. And even theoretically, you can prove that this is better than sampling with replacement. And choosing a larger mini batch size will give you a lower variance. But then again, you run into the problem that you have more complexity. Now, another thing that people sometimes do in practice is you don't wait for stochastic gradient descent to converge. That is, let's say you evaluate the gradient at each point, you don't wait until the gradient is equal to 0. Sometimes what people do is, well, you keep running, say, multi-epoch mini batch stochastic gradient descent. And also at the end of each epoch, you check for some validation error. So if the validation error sort of stops decreasing, then you stop SGD. You don't let it go on for much longer. It turns out, so this is one form of regularization, so to speak, and it's called early stopping regularization. So you stop SGD even before it converges, and that can often give you a much lower generalization error than allowing SGD to converge to a local minimum of the ERM. All right, because again, our goal is not really to minimize the ERM, but to minimize the generalization error. All right. So another thing in practice is that typically we have very large over-parameterized models. So the number of parameters or trainable parameters in the model is typically very large, millions, billions, these days even close to a trillion. And your data set is also just comparable to that of the dimensionality. Right? Because if you go by classical learning theory, then the number of samples that you need has to be at least a large factor times the number of trainable parameters. So if you have, let's say, 1,000,000 trainable parameters, you had better have at least, let's say, 100 million or 1 billion data points. But you don't have that in practice, right? You can compute the sample complexity for the problem, and that is the sample complexity will typically be very large. It's going to be at least, say, 100 times the number of trainable parameters. But if you want a small epsilon delta error, that's what the theoretical predictions will give you. But in practice, you don't have so much data, and you're typically in the regime where the number of data points is maybe roughly the same, or maybe a small multiple of the number of trainable parameters, sometimes slightly less than the number of trainable parameters also. So even in these cases, so in such cases, ERM has multiple global minima, as we just saw earlier, And some of these could incur a large population risk. The generalization error for many of these, even global minima, could be very large. But somehow in practice, SGD seems to find minima with low population risk. And it was not clear why it's doing so, but there are some theoretical works to show that for specific problems, SGD seems to do some form of implicit regularization. In fact, for some very specific problems, you can show that SGD, just plain SGD on ERM, does essentially the same as L2 regularized ERM, gradient descent with L2 regularized ERM on the L2 regularized ERM, or for some problems, it's the L1 regularized ERM and so on. It's not true for all problems. It's for very specific problems that this implicit regularization happens. But there's a growing body of work which shows that SGD can give better minima than gradient descent. All right, and multi-epoch SGD can do much better than single pass SGD. All right, so this is the reason why in practice what you typically do is multi-epoch SGD. All right. So again, if you go back to a recipe for training a machine learning model, we're given a hypothesis class and training and validation sets. So you first choose a smooth or surrogate loss function L prime, and now you fix a learning rate. Now this learning rate could be fixed. It could be something that varies with t. There are different learning rate schedules that one works with. We look at this in more detail later, and then try to do approximate regularized ERM using multi-epoch mini-batch stochastic gradient descent. Okay. Again, when I say mini-batch SGD, it's not sampling with replacement. It's typically sampling without replacement. So it's not SGD strictly speaking, but we'll just call it SGD. And then if you have some hyperparameters, let's say the number of hidden neurons, or even if you want to say choose the learning rate appropriately, you do so using a validation set, or you do k-fold cross validation. So that's going to be a recipe for training any machine learning model, right? And in addition, if you have the validation set, then you can also do early stopping. So you don't wait until SGD converges. You check the validation error after every epoch. If the validation error stops decreasing, then you stop SGD. All right. Great. So now we have a recipe for training any machine learning model, deep learning models in particular. But now everything boils down to how do we compute these gradients or stochastic gradients in every step. Okay. If I want to compute a stochastic gradient, then basically I want to evaluate a gradient of this particular form. So I have, let's say HW corresponds to a fully connected, whatever, 10-layer neural network. And I have some loss function, which is maybe the cross entropy loss, and maybe the L2, some L2 regularization or some other form of regularization. I need to be able to compute a gradient of this form. Or if the function is not differentiable, then I need to be able to compute the corresponding subgradient. Right. So now we'll try to address this particular question. Given a loss function and given some neural network or some function class, how do we compute these gradients efficiently? Any questions? So this brings us to one of the innovations that actually made training deep learning models practical. So this is called backpropagation, which is sort of a special case of a more general approach to finding derivatives of complex functions, complex and complicated functions. So again, what is the problem that we want to solve? We have some function L, which is of this particular form. I'll use this particular notation that capital W corresponds to all of the trainable parameters, and I have some loss function L, which could be the surrogate loss function also. For now, we'll assume that everything is smooth. Okay, but all of this can be generalized to the case where it is non-smooth also. You just replace, whenever I say derivative, you just replace it with subgradient. Now, again, there are two components to this particular loss function or objective function that I want to minimize. For simple regularization functions, which are typically either L1 or L2, the gradient or subgradient of G can be computed in closed form. That's not very difficult to do. All right. The difficulty is in computing the gradient or the subgradient for this first term, because, well, there's a very large number of parameters, and the function here itself is complicated. It's a composition of many functions, right? So in particular, what we'll specifically focus on is how do you efficiently compute the gradient of this first term, where HW is itself a composition of a very large number of simple functions, right? So again, the kind of hypothesis class or the function that we'll have in mind are fully connected neural networks with multiple layers, right? So you have the input data vector X, which is first multiplied with the matrix W1, and then you apply an activation function, and you keep doing this for maybe M layers. And our goal is to compute the partial derivatives of the loss function with respect to each of these trainable parameters. All right. So clearly, there's no we can't really hope to obtain some simple closed form expression. Right. And here again, this is a very specific case. In fact, it's a very nice and simple case because these are just simple matrix multiplications and activation functions. In practice, when we go to more complicated neural networks, let's say convolutional neural networks or other forms, this relationship itself gets more complicated to describe, right? But again, our goal is to compute the partial derivative. Always, the goal is to compute the gradient with respect to all of the trainable parameters, which is the same as computing the partial derivatives of the loss with respect to each of these trainable parameters. And again, when I talk about fully connected networks, just purely for notational convenience, I'll assume that there are no biases. But again, with biases, it's just you look at the augmented vector with 1 and then do everything correspondingly. This just keeps the notation simple. All right, so is the problem clear? So one very generic approach, which would work irrespective of whether you have these fully connected networks or any complicated function, is to just use numerical differentiation, right? Because we know that the partial derivative or the derivative at any point is obtained by taking the function f, perturbing the variable, the ith variable by an amount epsilon. So you do f of wi plus epsilon minus f of wi minus epsilon divided by 2 epsilon. If epsilon is sufficiently small, then this would be a reasonably good approximation for the gradient or for the corresponding derivative or partial derivative. And using this, we can compute the gradient. Okay. But so there are other approaches also you can do. So I use the symmetric central difference, but you could also potentially do f of w plus epsilon minus f of w divided by epsilon. But it turns out that this gives a better numerical approximation than the one-sided difference. So this is one approach which works for any generic function, right? All you have to do is, if you're able to efficiently evaluate the function f, then you can compute this gradient. But then what is the computational complexity? Let's assume that w is a d-dimensional vector. So you have the function f. So f is any generic function on d variables. And I want to compute the gradient. What is the computational complexity as a function of d? Like, how many arithmetic operations would I have to do as a function of d in order to evaluate one gradient? So would this grow linearly in D? I'm not worried about the exact constants involved, doesn't matter. But does it grow linearly in D, logarithmically in D, exponentially in D, or something else? Okay, someone says linearly in D. Other answers? Okay, what I want is a lower bound. Okay, there's at least I need to compute these many operations. If you want, let's be something more concrete. Let's just take a perceptron, for example, or two-layer, one hidden layer neural network. Yeah, let's keep that in mind. Let's just have a fully connected neural network. How many arithmetic operations, or a lower bound on the number of arithmetic operations required? So clearly it has to be at least linear in D, because I need to compute D partial derivatives. But is it just linear, or is it more than that? Okay, so to compute one partial derivative, how many I need to do two function evaluations, right? So each function evaluation, so the total number of function evaluations is 2 times D. That's the number of function evaluations I need to do, right? You all agree with me. Now, how many arithmetic operations are required for one function evaluation? Or at least how many arithmetic operations are required for function evaluations? Why, if it's D, why is it D? If it's D square, why is it D square? So remember that D is the total number of trainable parameters, right? So it's basically the total number of elements in the matrix, not the dimension of the input. Right? The number of trainable parameters would be quadratic in the dimension of the input. So the number of arithmetic operations, well, I need to at least multiply with each of the weights at least once when computing the function. So, and there are D weights. So the number of arithmetic operations includes at least D multiplications and a number of additions, perhaps. So the number of operations is at least omega D square to find one gradient. All right. Now, let's say that I want to train a model which has, I don't know, a billion parameters, because that's what we're interested in, right? If you take a standard large language model, then it has a billion parameters, or let's even take a million parameters, okay, which are relatively small models to train. So then how many arithmetic operations would I require? it's 10 to the 6 square, that's 10 to the 12, right? Which is huge. So once you go to say billion parameter models, so it's like 10 to the 9, I'll need 10 to the 18 operations. So you can see that this becomes computationally prohibitive even for reasonable sized parameters. Right? So even quadratic complexity is very expensive. And that was essentially one of the bottlenecks in training deep neural networks, because you have a huge number of trainable parameters. And if you just do plain numerical differentiation, then the number of arithmetic operations you require grows quadratically, which already blows up very fast. Right? So then is there a more efficient way to compute these derivatives? We'll build this step by step. So let's start with a very simple example of the perceptron. So the perceptron is where the prediction HW of X is just activation function of W transpose X. So the trainable parameters are stacked into one vector. We just take the inner product of the weights with the input and then apply an activation. Okay. Again, the activation, the choice of activation and so on depends on the problem that you want to solve, whether it's a classification problem or a regression problem or something else. And we'll take a generic loss function L. Now, let's say pictorially, this is what the perceptron would do. It takes this vector of inputs x1, x2, x3. It multiplies x1 with w1, x2 with w2, x3 with w3, adds them up, and then applies the activation function. Okay. I'm introducing these two new variables. So, and on this z, I'm going to apply L of z, comma, y, which is what I call f. So now I'm introducing these two new intermediate variables. So u is equal to w transpose x, and z is equal to phi of u. Okay. I'm deliberately introducing these new variables. I can sort of draw this from a different perspective, because in the end, I want to take partial derivatives with respect to w1, w2, and w3. So for this, let me depict w1, w2, w3 as my inputs. And w1 is going to get multiplied with x1, w2 is going to get multiplied with x2, w3 gets multiplied with x3, and these are added up to give you u. And then on u, you apply phi to get z. Okay. Again, I did nothing else except sort of redraw the diagram. Let's maybe keep this in mind. So I have w1, w2, w3, which are my variables. And I have u, which is another variable. And then I have z, which is my third variable. And I'm drawing these arrows to indicate that u is a function of w1, w2, w3, and z is a function of u. So given u, the z, to compute z, I don't need anything from w1, w2, w3. So u gives me all the information I need about w1, w2, and w3. So here I'm multiplying with x1, multiplying with x2, multiplying with x3, and adding it up. And on u, I just apply phi. Okay. And let me have another one, which is my final variable L, which is a function of z, and L of z is basically the loss evaluated on Z and Y. This could be my squared error loss or cross entropy loss or something else. Again, I'll assume that everything is smooth for now. So everything is differentiable. One thing to keep in mind is that in all of this, you can relax smoothness, but you will, that is, even if you don't have differentiability, it's still fine. But if it is not differentiable, then I'll want these functions to be convex so that at least a subgradient exists at all points. Okay, so now I want to find the partial derivative of L with respect to W1, with respect to W2, and with respect to W3. So let's use a standard high school approach and try to compute this using the chain rule. Because in the end, L is a composition of functions, right? You have W1, W2, W3. You first multiply with X, and then you apply phi, and then you apply this L, right? So let's find, say, partial derivative of L with respect to, say, W1. How would you evaluate this using the chain rule? Great. So first, you take the partial derivative of L, a little l, uh, with respect to z, right, and evaluate it at z times, it's the partial derivative of z with respect to, now z is phi of u, right? So this is, I can write this as dou z by dou u evaluated at u times the partial derivative of u evaluated at w1. Again, evaluated at the vector w, because u is now a function of w1, w2, and w3. Okay. So I've written this in a very specific form where I have these variables written up in different layers, and the variables in each layer depend only on the variables in the previous layer. And given the variables in the previous layer, they are independent of the variables that come before that. And therefore, I can write the partial derivatives in this form using the chain rule. Nothing else, just high school stuff, right? Similarly, I can write the partial derivative of L with respect to W2 y by dou z times the partial derivative of z with respect to u evaluated at u, and the partial derivative of u with respect to W2 evaluated at the vector W. In general, I could have the input dimensionality to be much larger. So I could have W1, W2, W3 up to some WD, right? It could be, say, D dimensional. And I could write an identical set of equations. Now, how does this scale? Now, let's say I'm able to compute each of these exactly, because I know the function phi beforehand. I know the loss function beforehand. So I can write a subroutine or a function that can compute the derivative of L, that can compute the derivative of phi. Maybe let's write it explicitly in that way. So this is equal to, let me call this, L prime of zy. Again, this is abuse of notation because I'm using L prime now to denote the derivative of L with respect to z. Times, now z is just phi of u. So this is phi prime of u times dou u by dou w1, which what is that equal to? Is just equal to xy. One thing to sort of uh, keep in mind is that this u is a function of x and w, and z is also a function of x and w, right? Because you're evaluating these functions at z. I'm evaluating phi prime at u, where u is equal to w transpose x and z is equal to phi of u for that specific w and for that specific x. Okay. So now what is, if I use the chain rule for this and try to evaluate the gradients, I can have a function or a subroutine that computes phi prime. I can have a subroutine that computes L prime. All right, because I can evaluate it in closed form because these are typically simple functions. So for cross entropy loss and maybe I don't know, softmax or some activation function, I can pre-compute I can have a function that computes all of these. So now how does the complexity of finding these subgradients scale with D? How many arithmetic operations are required? It's linear in D because all of it, I just have to do a small number of operations. In the specific case, to compute each of these, I just need to do 2 multiplications. All right. I need to sort of evaluate U and Z beforehand. That involves, again, an order D computation. But once I do that, finding each of these gradients is easy. It's just constant number of operations for each. That's again linear number of operations in total. And in fact, I can reuse some of these evaluations, right? Because this L prime, if you look at this first equation versus the second equation, they are the same except for the last term, right? Because this partial derivative with respect to z is the same in both terms. The partial derivative with respect to u is also the same in both terms, right? So what we can essentially do is, given a w, we can first use this w to compute u. You first compute u, you compute z, and you compute L, and then evaluate the partial derivative of L with respect to Z, the partial derivative of Z with respect to U, and then use that to compute the partial derivatives of, and you can compute the partial derivative of U with respect to W1, with respect to W2, with respect to W3, and then just some multiplications of these give me the overall partial derivatives, the partial derivative of L with respect to W1, W2, and W3. All right, let's see this in a slightly more complicated setting of a 2-layer neural network. All right, in this case, I have HW of X, which is phi2 of W2 transpose of phi1 of W1 times X. And again, we want to compute the partial derivatives with respect to each of these parameters. So I'll write it in the following manner. I have this matrix W1. All right, I multiply that with X to give me, say, U1, which is now a vector. And I take phi1 of U1 to give me Z1, which is again another vector of the same dimension. And I apply W2 transpose, which again are trainable parameters. And then I apply Okay, so I'm after multiplying with W2, I get, let me call it U2, and then I apply phi 2 to give me Z2, and then I apply my final loss function to give me L. My goal is to find the partial derivative of L with respect to each of the parameters W and with respect to each of the parameters in W1. So I'm assuming that W1 is a matrix. Okay? So again, dimensionality taken suitably. Okay? So I want to find dou L by dou W2 of, say, K, and the partial derivative of L with respect to W1 of K1, K2. So the K1, K2th entry of W1 and the kth entry of W2. All right. So the approach I'll use is the following. So the first step, which I call forward propagation, because in the end, we want to look at L as a function of W1, W2. Right. So given W1, W2, because they are the variables for my function, you compute the values of all of the intermediate variables. And you store them. So this include U1, Z1, U2, and Z2. Is there anything else? Yeah. And L, of course. Okay, so you get numbers for U1, Z1, U2, Z2, and L, depending on W1 and W2. Right? Next, starting from the right, you compute the corresponding partial derivatives. Okay, let's first find the partial derivative of L with respect to W2, with respect to Z2. So this is what is called backward propagation. Which is, so first you find the partial derivative of L with respect to Z2. Let me, just for convenience, let me call the computed values L tilde, Z2 tilde, U2 tilde, Z1 tilde, and u1 tilde. So these are the intermediate variables. And for the given w1 and w2, so let me use the tilde to denote the specific values at which I want to evaluate the derivative. And I'll use w1, w2, u1, z1, u2, z2, l to denote the variables. All right. So without the tilde, it's just the generic variable itself. And the tilde denotes the point at which I evaluate these functions. So first I compute dou L by dou Z2 at the point Z2 tilde. Let me call this say Z2 bar. I get some number. So this is basically the partial derivative of the loss function with respect to Z2 evaluated at this point Z2 tilde. I get some number. I'll call it Z2 bar. Right. Next, I'll go to the next layer. I've evaluated something with respect to Z2. I want to compute that the partial derivative of L with respect to U2. So next, compute U2 bar, which will be the partial derivative of L with respect to Z2, evaluated at Z2 tilde, times the partial derivative of Z2 tilde, sorry, of the partial derivative of Z2 with respect to U2, and this is evaluated at U2 tilde. This, as you can see, just by the chain rule, this gives you the partial derivative of L with respect to U2 evaluated at U2 tilde, right? Which is just Z2 bar times the partial derivative of Z2 with respect to U2 is phi 2 prime of U2 tilde. Now again, you have a subroutine that computes phi 2 tilde. You can write a function that does so, and that's all. Now having computed this, you compute say want to compute W2 K for K equal to 1, 2, 3 up to the dimensionality of W, which is again the partial derivative of L with respect to Z2 evaluated at Z2 tilde times the partial derivative of Z2 with respect to U2 evaluated at U2 tilde times the partial derivative of U2 with respect to W2K evaluated at this entire vector W if required. The product of the first two terms is basically just U2 bar. Right? Effectively, it is just the partial derivative of L with respect to U2 evaluated at U2 tilde. So in a sense, to compute the partial derivative with respect to W2, all you need is a partial derivative of L with respect to U2. Everything beyond that is really unnecessary because of this structured framework. So this is just U2 bar times the partial derivative of U2 with respect to W2K evaluated at W tilde. All right, since it's just matrix, since it's just an inner product, this will just be equal to, I think, Z1 of K. This is U2 bar times Z1 of k. Right? I can. So now I've computed all of the derivatives. Let me call this W2 tilde of k. And the same, it's just the same as we go along. You can compute the partial derivative with respect to z1. Similarly, you compute z1 k, which will just be w2 tilde k times the partial derivative of um, I guess w2 tilde k okay, I have to be a little more careful here. This gives me the partial derivative of u1 with respect to z1k. So let's sort of maybe write this explicitly. So this is supposed to be the partial derivative of L with respect to z1k, which is equal to the partial derivative of L with respect to u2 times the partial. Now u2 is just the inner product between z and w2, right? So this is this times the inner product between L, sorry, which one? Yeah. So these are vectors, right? Z1. So the partial derivative of L with respect to U2 times the partial derivative of U2 with respect to Z1 tilde. Questions? Right. So I'm sorry. Oh, sorry. Yeah, this should have been a W2 bar. That's correct. All right. And in a similar fashion, right? So this would just be equal to U2 bar times dou U2 by partial Z1k evaluated at Z tilde. So I leave it as an exercise for now to complete the rest. find the partial derivatives with respect to u1 and with respect to w1. Now there should be a slight tweak in this structure over here. This wasn't done very well. So really what I have is I have Z1. So U2 is equal to inner product between Z1 and W2. Right? So it's not that W2 depends on Z1. It is that U2 depends on Z1 and W2. Okay. So using this, complete the rest of the partial derivatives, and we'll continue in the next class.